Hi everyone, my name is Sanjay Chouhan and welcome to my YouTube channel. So in this NLP series, in the last video, we looked into text representation using frequency-based approach. So text representation means converting the text into numerical form so that we can train machine learning models or do any kind of analysis. So in this video, we'll look into text representation using another approach called prediction-based embeddings. So in the prediction-based embeddings, we have few techniques. We'll look into the few of the important ones. So the first one is the Word2Vec embedding or Word2Vec technique. The Word2Vec is a machine learning model which gives you a dense representation of a word, and the representation of the word is of fixed size. So as the name says, Word2Vec. So it converts the word or it gives you vector representation of a word. Here you can see the example. So for the word cat, we are having this vector representation, and the vector representation will be dense. That means it will not have zeros. As we saw in the last video, for frequency-based approaches, we usually have lots of zeros in the vector representation. But in the prediction embeddings, we don't have zeros. All the representations are dense, and we usually have a fixed size representation. Whereas in frequency-based approaches like Vega or TF-IDF, the dimension of the vector is calculated based on the number of unique words or based on the number of vocabulary, which is dependent on the data that we provide. But in prediction-based embeddings, like Word2Vec, the dimension of the vector is predefined, and um, and and it's usually dense. For this word cat, we are having this representation. For kitten, we are having this representation. All of them are dense, and all of them are decimal point numbers. The Word2Vec will take care of semantic similarity. So that means the words which are similar are going to be nearby. So here you can see cat and kitten are similar words, so they are very near. And dog and cat are very similar as well because both of them are pet. So those are also similar. Whereas the houses is very different from these animals. So the distance between these uh, animals and the houses word is very far. So the word back will take care of the semantic similarity of the word. And in the next example, we'll see that we are having man, woman, king, queen. Yes. So it also take care of analogical reasoning. So if you see, if you plot this man, woman, king, queen on 2D surface, you'll see that men and women are having so the direction between men to women, the direction from men to women will be same as the direction from king to queen. So we see that these are parallel. And similar thing can be seen with country capital relationship. The word to vector models can be trained using our own data. So it's a model architecture is available. We can use the model architecture and train the word to vec model on our own data. But there are already trained models available on the internet, and we can make use of that models. So one of the popular one is the Google News Word2Vec model, which was trained by Google on their news data, and it produces a vector representation of dimension 300. So we'll see that in example. So Word2Vec provides a vector representation for individual words, aka word embedding. So it will provide an embedding or vector representation for a single word. So given a sentence, it won't provide you the vector representation of the sentence. Like in Beggar word, we are getting the vector representation of the whole document. But here you will find a vector. Here you will only get the vector representation of each of the individual word. So to get the vector representation of the sentence, what you need to do is you need to get all the vector representation of all the words present in the sentence and take a average of that. So that's the usual approach that is followed in the NLP. And there is one more model called Glob. So it's also similar to Word2Vec model only. It was trained using a something using a different technique, but it's also similar to Word2Vec model. So you can use either one of them. Okay, so let's look into the example on IPython notebook. So here we need to install the Gensim library, using which we'll use the Word2Vec model. So we will run the pip install Gensim command to install the Gensim library. And since we don't we need to download the model. You can search for Google News Vector, or you can search for Google Word2Vec model. You'll find the uh, zip file or the model file on internet. You can download that and use from. You can download locally and then use. So here, what I have done is I have downloaded and stored on my Google Drive. So I can just connect to my Google Drive using this Google Colab module, and then I will be able to access the I'll be able to access the Word2Vec model. So the model is stored at this location. You can see if you run this ls command, see that it's available, and we'll import the git vectors, function from this Gensim models in module. So we are downloading we're importing this module. Then we'll provide the path of the model in this load Word2Vec format function. Once we run this, the model will be loaded. So this command will load the model. Once the model is loaded, we'll be able to make use of the model. So model is loaded in this variable model. So to get the vector representation of a word, we just need to call the get vector function from the model object, and we need to provide the word that for which we want to get the embedding or vector representation. So the vector representation is also called embedding. So I'll use the embedding and vector representation interchangeably. We are getting the vector representation, and we are saving in this embedding variable. You see that the shape of this embedding is 300. Okay, so the dimension or the length of this embedding is 300. You can see that in the name of the file as well. So the Google News vectors negative 300. So here 300 means the dimension is going to be of 300. And we can print this is the vector representation of the word happy. So you can see here is that the representation contains uh, decimal numbers, and we are not having zeros. So it gives a dense representation. We are not having zero means we are not having any sparse data. We are having a dense representation, and all the elements in the vector are going to be decimal point numbers. So the dimension here is 300. If you want, we can take a lesser dimension as well. So if you want to take only the first 20 elements from this representation, that is also allowed. So this is just array slicing, where we are taking only the first 20 first 20 elements from this array. If some word is not present in this model, that is also possible. Some rarer words or some mistyped words might not be present in the model. In that case, the model will return key error. So in this model, we'll be able to get similarity between two words. So here we are given dog and puppy. We want to get a similarity. So the similarity will range from 0 to 1. 0 means no very dissimilar, and 1 means very similar or same. So the similarity score between dog and puppy is 0.81, which is a very high number. As we know, these two words are very similar. And the similarity between dog and cat is 0.76. which is slightly less than dog and puppy, which is expected. And the similarity between dog and book is going to be very, very low because these two words are not similar at all. So that similarity score is 0.08, which is a very low number. We can also get most similar words. So given a word, we can get the top and most similar words. So here I'm saying to get the top 5 similar words uh, related to burger. So the top similar words related to burger are, it's taking some time. Okay, the top similar words are burgers. So it's a plural form of burger. So the similarity is 0.82. Then hamburger, cheeseburger, sandwich, and burrito. So all of these are food items which are very similar to burger. Now we have seen that we are able to get the vector representation or the embedding of a word, but in real life, you need the vector representation of a document. Document can be the review or some kind of paragraph. So to get the vector representation of a document, what you need to do is get the vector representation of each of the word and take a average. So here we'll see this is a document or sentence. The child makes the dog happy, which we saw in the last video as well. So we can get the vector representation of this document by getting the vector representation of each of the words. So in this function, what we are doing is first we are getting each of the word by splitting them, and then for each of the word, we are checking if the word is present in the model or not. If it is present in the model, then we'll get the model vector representation of the word from the model. So we can use this, or we can call the get vector command as a get vector function as well, or we can directly use like we do in dictionary. So this will give you the vector representation of this word, and we're appending everything in a list, and then we are calling this numpy min function to get the average of this list of embeddings. So this will give you the sentence embedding using the Word2Vec model. So here I'm calling the sentence embedding, passing the sentence for which I want to get the vector representation, and passing the model, loaded the model. And once I run it, I'll able to see that the embedding is of 300 dimension because we are taking the average, so the dimension will remain same. As earlier, we'll be able to make use of first n dimensions as well. So the sentence BERT is a BERT-based model which gives you embedding for sentence. So BERT is a transformer-based model. The sentence BERT gives you a semantic sentence embedding. That means the semantic meaning of the whole sentence is preserved in the embeddings. It captures the semantic similarity between sentences. So given two sentences, if they are using different words but they are semantically similar, then the embeddings will be closer, and it outperforms the simple averaging of word embeddings. So we have seen that we can take average of Word2Vec embeddings to get the sentence embedding in Word2Vec technique. But the sentence embedding gives you the embedding for the whole sentence. So we don't need to take any average or anything. And the sentence embedding is much, much better than the average Word2Vec technique. So before using the sentence BERT, we need to install the sentence transformers library from pip. So we are installing we are running the pip install sentence transformers command to install the sentence transformer library. Once once the sentence transformer library is installed, we can import it, and then we are initializing the class of sentence transformer, and we need to pass the model name that we are going to use. So there are various pre-trained model available on in sentence transformers. So we are using this all MPNet base V2. So you can see all the pre-trained models on the documentation page of the sentence transformer. So here you can see we are having this all MPNet base 2, and there are other models as well. And various details related to the models are present here, like the scores, the model produce on different result, different performance analysis, and the speed, size of the model as present here, and some other details. If you click on the model name, you'll see some other details like what is the dimension of the embedding that it produces. So the all MPNet base V2 will produce sentence embedding of size 768 dimension. Uh, yeah, so this is what we are using, all MPNet base V2. So we have this sentence: the child makes the dog happy. Okay, this is our sentence or the document one, and we can just call model.encode and pass the document into the model to get the embedding. Okay, so this is the embedding. Let's see the shape of the embedding. As you can see, the shape is 768, as it was mentioned in the documentation page. So we can also view the embedding. So you can see here, this is also a dense vector. That means all the values in the vector are present. Okay, we are not having any zeros here. This is dense vector, and it is containing decimal point number. Just like the word embeddings, it's dense and it contains decimal point numbers. So this is the 760 dimension for the sentence. The child makes the dog happy. Okay, so let's look into one more example of the sentence transformer. So let's suppose, okay, we are here we are initializing the sentence transformer, and with a different model. So this is a multi QA MPNet model. This is a model for question answer. Okay, so it was trained for question answer. So we have a query that is a question like how big is London? And we have various sentences. Okay, I mean 3 sentences we have, and we need to see which of the sentence can answer the question that is asked here. So we have query embeddings, and then we have passes embeddings, and we need to see which of the passes embedding is related to the query, which of the sentence can answer the given query. So we get the embedding for query, get the embedding for all of the sentences, and then what we do is we take a similarity between sentence embedding and passes embeddings. So let's first calculate the embeddings. Let's download the model. Okay, so we'll see the dimension of the query embedding, 768 dimension, because it's a query. How big is London? And then the passes embedding shape is 3 into 768. So we have 3 passages here. So for each of them, we have vector representation of dimension 768. Now we can calculate the semantic similarity between query and passage embeddings to get the related passage for the given query. So in the model, we have this feature called we have this function called similarity. You can call model of similarity, pass the query embedding and the passage embedding to get the similarity score. So let me just print the similarity here. You can see the similarity are present here. So between the query and the first passage, the similarity is 0.4556, and the query and the second passage is 0.614842, and query and the third sentence in the passage is 0.2697. So the highest one is 0.6142, which is for the second sentence in the passage embeddings. Okay, so you can see the second sentence or second passage here is London has 9 million some in evidence at the 2011 census. Okay, so this contains the number of people live in London according to the 2011 census. And our question was, how big is London? For this given query, the second basis is giving the answer. That's why we see the higher similarity between the query and the embedding of the second passage. So till now, for text representation or text vectorization or converting text into numerical form, we have seen multiple approaches. We have seen traditional techniques like bag-over, TF-IDF, and then we saw model-based techniques like Word2Vec and sentence transformers. The sentence transformer is performing the best out of all the embedding models or all the text vectorization techniques that we discuss. And based on the project need, we might go with the sentence embedding or we might go with some traditional technique like bag-over. And also, there are better sentence embedding models as well. We have seen here is from very old sentence embedding model. This is SentenceBERT. But it's still used and it's still very good. But there are some better techniques like there are from LLM which are giving more dimensions than 768. Here we're getting 768, but there we can get more in thousands, and it's going to be containing more information because those are coming from bigger models and those are trained on bigger data set. So you can search for like OpenAI embeddings. You'll see that OpenAI also provides some embedding models which are giving embeddings for sentences, paragraphs, and it's going to be in thousand or like 1500 or 2000 dimension, but it will have more information as compared to this. Thanks for watching.